So my name is Hafiz, and my other roommate is Amirul, Danish, and me. So we are from Group 3. Today we're gonna present about pre-stressing. So what is pre-stressing? Pre-stressing involves pre-compressing concrete that enhance the performance of the structure. By applying attention to the reinforcement bar, it effectively reduces tensile stress, prevent potential crack, and improve structural integrity. So at the right side is the how pre-stressed concrete work. And the first picture is about conventional in situ casting, and the second answer is about pre-stress, how pre-stress work. Materials in pre-stressing. So in pre-stressing there is high strength concrete and also high strength steel that being applied tension. So this is where the pre-stressed concrete when applied. So first is bridge. So for building bridge can be durable and efficient, high load capacity, and also to control the crack and also to reduce the maintenance. Second one is at the building, modern architecture, and also large column to free space, and also to make a steam slab, and also can reduce building height. The last one is tank. So when the using a pre-stress, the water storage can ensure the water airflow can keep concrete compressed, so we can prevent concrete from forming or deflect.
Pre-stressed concrete beams. What exactly are they? How are they made? And why are they useful? Before we explain, it's necessary to provide a brief overview of traditionally reinforced concrete beams for comparison. Concrete is very strong in compression, but only 1/10 as strong in tension. So if we make a beam of pure concrete and apply a bending load, the top half gets compressed while the bottom half is in tension. This tension zone in the bottom half will form cracks that propagate until the whole beam fails. This is where reinforcing steel comes in. Primary structural bars are generally placed in the tension zone. So, when the concrete cracks, the reinforcing steel takes the tension load. There are other types of bars, such as for controlling thermal effects, but that's beyond the scope of this video. It's also worth keeping in mind that the tension zone is not necessarily always on the bottom. For example, near a column or at a cantilever, the tension would be in the top and compression in the bottom. Traditionally reinforced concrete essentially combines steel and concrete and then lets it act as it would passively, compared to pre-stressed concrete, which actively engages the materials. Now let's contrast the traditionally reinforced concrete beam to a pre-stressed one. We'll look first at precast, pre-tensioned concrete. For this beam, first, the cables are placed in a form, and then they're tensioned. Next, the concrete is poured, and then allowed to cure. Once cured, the cables can be released from the tensioning forms. Now, the pre-stressed cables will contract. This induces compression in the bottom half as part of manufacturing, sort of like a cambering effect. Once the beam begins taking load, it still applies tension on the bottom half, but this time, the tension has to cancel out some pre-stressed compression before creating a zone of net tension. In this way, the pre-stressed beam is able to take more load than the traditionally reinforced concrete one, all else equal. The amount of pre-stressing has to be carefully calibrated to avoid tensile cracking on the top with too much pre-stressing, but also must be enough to avoid concrete shrinkage depleting the pre-stress over time as the concrete cures. Early pre-stressed concrete designs made the mistake of not properly accounting for concrete shrinkage. As concrete cures, the water inside it evaporates, and this causes shrinkage, which can occur for up to 18 months of curing. Let's examine how this shrinkage would impact our pre-stressed beam. As the concrete shrinks, so too would the pre-stressed steel bonded to it, which reduces the tension force in the steel, and thus reduces the pre-stressing load. So, in order to offset the losses of shrinkage, you need more pre-stressing. But, at a certain point, you'll rupture the steel if you pre-stress too much. That's where high-strength steel reinforcing comes into play. About 100 years ago, designers of concrete structures realized that in order to properly utilize high-strength reinforcing, it needed to be pre-stressed. This led to a lot of development in material science for high-strength reinforcing, as well as for high-strength concrete. Today, prestressed concrete generally uses both high-strength reinforcing and high-strength concrete in order to maximize the benefits of prestressing. We can't discuss prestressing without also discussing post-tensioning. Post-tension concrete is a similar active combination of concrete and steel, also generally using high-strength materials. But for post-tensioning, the pre-stress is applied on-site after concrete has cured, but before the structure sees its anticipated design loads. Post-tension reinforcing tendons are carefully draped throughout slabs and beams to achieve the desired bending and deflection criteria. Post-tension tendons can be either sheathed and greased or unsheathed, which have different benefits for load transfer, ease of construction, or replacement, and weatherability. But that's a deep dive for a whole separate video. The main benefits of prestressing generally stem from the fact that it actively engages the steel and concrete. This results in a stiffer section that presents options to use less material, allow longer spans, or carry additional load. Of course, these benefits come at the cost of added design and construction complexity, so use depends on the specific application. If this brief introduction to prestressed beams was interesting for you, let us know your thoughts in the comments. We also welcome your ideas for future video topics, and we're always curious to know what topics you'd like to see a deeper dive on. And if you like these videos without sponsorship ads, consider buying us a coffee with the link below. We also appreciate every like and subscribe. Thank you very much, and see you next time.
In this slide, I will be explaining about the two methods of prestressing, which is pre-tensioning and post-tensioning. Let's start with pre-tensioning. In this method, steel wires are stretched first before the concrete is poured. Once the concrete hardens, the wires are cut and tension from the steel is transferred to the concrete. This method is usually done in factories and it's commonly used for precast elements like beams and floor slab. You can also think of it like stretching a rubber band before freezing it inside the concrete. Next, we have post tensioning. Here, the concrete is poured first with empty ducts inside. After the concrete was hardened, steel wires are inserted into the ducts and pulled tight. The wires are anchored at both ends and the ducts are later filled with grout for protection. This method is usually done on site, especially for large structures like bridges and buildings. And you can think of it like tightening the steel inside the concrete after it was hardened. In summary, the difference is the timing of when the steel is tensioned. Before casting for pre-tensioning and after hardening for post-tensioning.
Why is prestressed concrete preferred compared to the conventional in situ construction method? First, it improves durability and lower maintenance. So prestressing reduces cracking, so limit to the corrosion pathway. Compressive stress is applied to keep the concrete in compression, prevent the tensile crack from forming. So crack are the main problem, which is where the water, oxygen, and the chlorides can entry to the cracks and give a chance of the corrosion instead of tendons. Better quality control and during manufacturing. So when produced in a controlled factory environment with a skilled workers to ensure the proper curing is designed and uncover thickness to reduce the corrosion potential. Second is increase the both ultimate and service load capacities. Reducing can increase the moment capacity and ultimate load capacity of beams compared to the non-stress reinforced concrete. It allows the steel and concrete to work more efficiently together, utilizing the full strength of both materials. Height stiffness. Prestressing increase the moment capacity and ultimate load capacity of beam compared to non-prestressed reinforced concrete. Prestressed concrete behave as a composite system with the height, stiffness, and significantly reduce the deflection under the service and ultimate loads, making it more suitable for build to the structure of the longer span and height load structural application than the conventional in situ concrete. So the different prestressed concrete beam
can go for the longer span, which is 25 to 45 meter span, and then reinforced concrete beam basically go to 10 to until a 15-meter span. The stress concrete also have disadvantages. Firstly, to do the precise concrete, we need require skill and focus. The installation of pre-stressed concrete requires a specialized knowledge and training. Skill labor is essential to ensure that the tendons are accurately placed and tensioned, which directly impacts the structure's performance. Second, it costly materials. Prestressing involves the use of high-strength steel tendons and concrete, which can be significantly more expensive than the traditional method. This higher initial investment may deter some projects, especially those with a tight budget.
Pre-stressed concrete on SDG. Pre-stressed concrete is more focused on SDG 9 and 11. These both are for resilient infrastructure, which is a high strength, high durability, high ductility, and high serviceability limited. Pre-stressed concrete is more resilient compared to conventional method. In some cases, it was 4 times stronger than conventional method. Next is promoting inclusive and sustainable industrialization. The concrete is lighter, thinner, and less material needed in the making process, mean lower carbon emission, but still getting a higher durability product. A company called Holcim claimed that their pre-stressed concrete reduced CO2 emission by up to 75% compared to conventional method. And lastly is fostering innovation and technological development, using advanced material and technologies in the process of making pre-stressed concrete, such as high-strength concrete and high-tensile steel for tendon.